Welcome. In this video, we continue Chapter 4, Applications of the Derivative, and today we look at 4.7, L'Hopital's rule. This is a method for computing some tricky limits. L'Hopital's rule is a trick for evaluating certain limits. Let's take a look at a very simple limit, and we'll do it the old way, the way that we already know how, and then we'll do the same limit in the new way, using L'Hopital's rule. Okay, the old way says, let's factor the top and the bottom. Do you see how the top factors? How does that numerator factor? It factors as x minus 2, x plus 3. And now I notice, there's a common factor above and below. Those cancel, leaving me with the limit as x goes to 2 of x plus 3. Now I can actually plug in the 2, and I end up with 5 as my solution. The new way, L'Hopital's rule, this says, take the derivative of the top and take the derivative of the bottom, and the limit will be the same. It's a little surprising. There doesn't seem to be any reason why I should think this works, but in fact it does. So the derivative of the top is 2x plus 1. The derivative of the bottom is just simply 1. And I now take the limit, again, the limit as x goes to 2. And now I can just simply plug in the 2, and I find that my solution is 5. It's kind of remarkable that this works, and it really does. If I have this kind of a fraction, just take the derivative of the top, take the derivative of the bottom, it gives me a new limit problem, which is simpler to solve. Here is the statement of L'Hopital's rule. If the limit as x goes to a of f of x over g of x has indeterminate form 0 over 0 or infinity over infinity, then the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x. So indeterminate form, 0 over 0, what do I mean by that? What I mean is, suppose we're given a limit problem, if I were to just plug in the x value right away, in this case, if I were just to plug in 2 for x, what would I get? Well, 2 cubed is 8, and then minus 2, and then minus 6, that's on top. And if I were to plug in 2, I get 8 minus 6 minus 2. Oh yeah, so that's 0 over 0. So that's what I'm talking about, that if you actually just plug in the x and you get 0 over 0, then that's the indeterminate form. Okay, this problem has indeterminate form 0 over 0, so let's solve it. Now, you could solve it the old way by factoring the top and factoring the bottom. I'll give you a moment to do that if you would like. Or we could use L'Hopital's rule and simply take the derivative of the top and the derivative of the bottom. And so I still have the limit. Don't forget to keep writing limit. It's easy to forget, but it's still a limit problem. The limit as x goes to 2. Now it's 3x squared minus 1 over 3x squared minus 3, right? And now it's pretty easy to plug in 2 for x. 3x squared is, well, 3 times 2 squared, that'll be 12. So I have 12 minus 1 over 12 minus 3, 11 ninths. Here's an example where the indeterminate form is infinity over infinity. So a couple new things here. First of all, notice I'm allowed to approach 0 from just one direction. Approaching a is all right, from either direction, from the left, from the right, or from both is fine. What do these functions look like? So let's take a look here. Here's the natural log of x. So the natural log of x looks something like that. But in the numerator, I'm looking at negative of the natural log of x. So imagine flipping that over, something like that. So here we go, negative natural log of x. So you can see this limit as x goes to 0 from the right, negative natural log of x climbs higher and higher and higher, and it goes to infinity. What about the denominator? 1 over x. So here's a picture of 1 over x. And if I approach, again, 0 from the right, then the values of 1 over x grow larger and larger and larger without bound. So this really does have indeterminate form infinity over infinity. Now, the question almost becomes, which of these goes to infinity faster? If the top goes to infinity faster than the bottom, then the answer to the whole fraction will be infinity. But if the bottom goes to infinity faster than the top, then the solution to the whole thing will be 0. Which is it? Do you think you know? Let's find out. All right, so I don't think there's any way I would be able to know how to do this other than just using L'Hopital's rule. So let's take the derivative of the top and the bottom. I get the limit as x goes to 0 from the right, negative 1 over x divided by negative 1 over x squared. Do a little bit of algebra, do a little more algebra, and we find that the solution is 0. Take a little care, all these equals signs in here. What am I doing for each of the equals signs? In the first case, that's the actual application of L'Hopital's rule. And then there's some algebra, and then finally I'm evaluating the limit. That's why LIM keeps appearing on and on and on. I haven't evaluated the limit, but then at the very end, the last equality is when I evaluate the limit, so the LIM disappears, and all I'm left with is the actual number. How about some limits with trig functions? Why not? The limit as x goes to 0 of 1 minus cosine of 5x over 8x squared. What is the indeterminate form here? Well, notice that the cosine of 0 is 1. So in the numerator, I have 1 minus 1 over 0. Oh, okay, so that's 0 over 0. So it does have indeterminate form 0 over 0, so I can use L'Hopital's rule. Take the derivative of the top, take the derivative of the bottom. Notice my function was negative cosine, so the derivative of negative cosine is positive sine. But notice that a 5 comes out because of the chain rule. The derivative of 8x squared is, of course, 16x. So now I just plug in my 0 for x, right? And what do I get? 5 times the sine of 0, oh, that's 0 over 0. So I can't plug in x. What am I to do? Well, of course, right? Of course, it's just 0 over 0 again. In fact, I can apply L'Hopital's rule a second time. So let's take another derivative. And I get now another factor of 5 coming out. The derivative of sine is cosine, so I have 25 cosine 5x, now all divided by 16. I think at this point, if I plug in 0, cosine of 0 will be 1. So 25 times 1 over 16, now I get 25 over 16. So there is something that happens occasionally. You may need to apply L'Hopital's rule more than once to solve a limit problem. Let's do another limit problem with trig functions. And this shows one more thing that we might come across with limit problems. What is the indeterminate form here? X squared times cosecant of x squared. Well, there's no way it can be 0 over 0 or infinity over infinity, right? Because this is just a product of two things. Until we remember, oh yeah, cosecant of x squared is really the same thing as 1 over the sine of x squared. So this often happens with trig problems. With L'Hopital's rule, you might need to play around and find some different ways of expressing your trig function so that you can put your main expression in terms of a fraction. So here we go. Rewriting cosecant x squared as 1 over sine of x squared. Now we have the fraction x squared over sine x squared. What form is this? This looks like the form 0 over 0. So I can use L'Hopital's rule, take the derivative of the top and the bottom. I get the limit as x goes to 0 of 2x over cosine of x squared 2x. Now, you might be tempted to think that this is form 0 over 0, but we don't, and we could do that if you want to, but more easily, let's just cancel out those common factors. And this turns it into the problem of finding the limit as x goes to 0 of 1 over cosine of x squared. And cosine of 0 is 1, so this becomes 1 over 1, which is just 1. Let's take a second and talk about why does L'Hopital's rule work. And here's our proof for the indeterminate form 0 over 0. In this case, the f of a, that was the function on top, evaluated at a, and g of a, the function on the bottom, evaluated at a, both of those equal 0. We start off with the limit problem, limit as x goes to a of f of x over g of x. And I can rewrite this as f of x minus f of a over g of x minus g of a, because after all, f of a is 0, g of a is 0. I'm not really changing the problem. And then let's take that numerator and divide by x minus a, and the denominator and divide by x minus a. It seems like a little strange thing to do, but this x minus a, that'll be an actual number. There's no danger of it actually equaling 0, because my limit is the limit as x approaches a. X gets close to a, but x never actually equals a. So, okay, it looks like I'm making this problem a lot worse though, right? I'm going from something simple to something complicated. Well, one thing, even a little bit more complicated, let's take that limit and put it up above and below, because the limit of a quotient is the quotient of the limits. All right. Well, do you recognize something now? What does that top look like? What does that denominator look like? Maybe the derivative of f evaluated at a and the derivative of g evaluated at a. And now we can pull out a limit as x goes to a, and just call that f prime of x over g prime of x. So it's very clever. It's just a short string of equalities, but it's very clever how we got from the beginning to the end, and this shows how L'Hopital's rule works. Using derivatives, using the definition of the derivative, that's kind of neat. Let's continue on. I have one more example. I just want to show that it's allowable for us to take a limit as x goes to infinity as part of L'Hopital's rule also. So let's try this one, the limit as x goes to infinity of the natural log of x over 2 times the square root of x. Let me just draw little pictures first. Natural log of x looks something like that, and the square root of x, or how about twice the square root of x, looks something like that. 2 square root of x, natural log of x. And the question almost becomes, which of these grows faster? They're both going to infinity, so this is indeterminate form infinity over infinity. But if the natural log of x grows faster, then the answer to this problem will be infinity. But if 2 root x grows faster, the answer to the limit problem will be 0. So let's find out which function grows faster. L'Hopital's rule, let's take the derivative of the top and the derivative of the bottom, and keep the limit. Now I have the limit as x goes to infinity of 1 over x divided by 1 over square root of x. Let's do a little algebra. I get the limit as x goes to infinity, square root of x over x. Maybe a little bit more algebra. Now x is positive because x is going to positive infinity. So x equals the square root of x times the square root of x. So I have 1 factor of the square root of x on top, canceling with 1 factor of the square root of x on the bottom. And that leaves me the limit as x goes to infinity of 1 over the square root of x. And now I can see pretty quickly what the answer to this is. That denominator grows larger and larger and larger without bound. So this limit is 0. And that's L'Hopital's rule. It is a really neat method for computing some tricky limits.